On lesson 16, we're going to be dealing with rational graphs. Rational graphs are graphs of equations like y equal 1 over x. That's the parent function of a rational graph. Now, it's going to look something like this, and this is just a quick sketch, but it's going to turn in here and turn in there. What we've been dealing with is polynomial functions. That's where there's not a variable in the denominator and there's not a variable in a square root. And so we dealt with odd and even leading coefficients and how that would look with the end behavior and all that. So we're really dealing with rational graphs in lesson 16, but in this homework I've thrown all kinds of stuff in here to review. Now, one thing we got to look at here is it says name the asymptotes if there is an asymptote. There may not be one. There's not going to be one if it's linear or if it's a polynomial function. We don't have an asymptote. We'll have an asymptote if there is a rational function. Now, in the parent function, what we're saying an asymptote is that's a line that your solutions seem to be approaching but never crossing. Can you see that those red curves, they seem to approach the y-axis but never cross that? So we call that an asymptote, okay? Asymptote. And then they seem to be approaching the x-axis and never crossing. And so we have a vertical asymptote at x equals 0, the vertical line x equals 0, which is the y-axis. We have a horizontal asymptote at y equals 0. That's the horizontal line y equals 0, which is the x-axis. Now, if we go back to the idea of changes in parent function stuff, then here's what we want to think. This is actually like x plus 0 understood to be in parentheses plus 0. That means that there's no horizontal shift and there's no vertical shift. And so our asymptotes are at the x equals 0, y equals 0. If we were to change that to y equal 1 over x and then we were to add 2, there would be, what would happen? It would shift up 2. I think I said that backwards. Vertical shift, horizontal shift. Maybe I said that backwards a while ago. I don't remember how it came out of my mouth. But anyway, just in case that's a correction. So that would cause it to shift up 2. So instead of your horizontal asymptote being y equals 0, it would become y equal 2, and that whole curve would shift up 2. You see, it would begin to approach that asymptote rather than the other one, okay? Okay. If I had y equal 1 over x minus 2 like that, then that is affecting x inversely. As in other words, instead of a minus 2, we're going to undo with a plus 2. So it's like you're going to increase x by 2. So it would shift to the right 2. Shift right 2. So instead of the asymptotes being the x and y axis, if it shifts right 2, instead of your vertical asymptote being x equal 2, x equals 0, it would then be x equal 2, and so then your curve would approach those asymptotes rather than where they were to begin with, okay? So there's the general idea of the asymptotes of a rational function, and thinking back to our parent function transformations and how that would shift the whole graph, which would also shift the asymptotes, okay? All right, but before we get to one of those problems or some more of those problems, then we're going to have all kinds of other things thrown in there just to review our brains. Okay, so here's the directions. Given the equation, give the equation for the asymptote if the graph is rational. Build an appropriate table of values and then graph the function. Well, the first equation is what? It's linear. It's of the form y equal mx plus b. So it doesn't have asymptotes. To build a table, we start with x because it is the domain or the independent variable. We solve for y because it is the range or the dependent variable. What it says y is equal to goes in the middle. I'm quoting page 97A of my algebra book. And then we said if the slope is a fraction, then we're going to choose multiples of the denominator for x. Remember that? So we're going to be very careful of the x's that we choose as we get into some of these more complex graphs. Okay? Now, we're going to plug those x's in. So we're going to have negative 2/3 times the x of negative 6 plus 4, and so on. So we're going to plug in those x's and solve for the y's. So 3 goes into negative 6. Negative 2 times negative 2 is 4 plus 4 is 8. 3 goes into negative 3. Negative 1 times negative 2 is 2 plus 4 is 6. Anything times 0, 0 plus 4 is 4. 3 goes into 3. 1 times negative 2 is negative 2 plus 4 is 2. 3 goes into 6. 2 times negative 4 is negative 4. 2 times negative 2 is negative 4 plus 4 is 0. Now, we should know that what we have here is the point negative 6, 8. We have the point negative 3, 6. So we created points that we could graph, right? We have created the point 0, 4 that we could graph. We have created the point 3, 0 that we could graph. We have created the point 6, 0 that we can graph. We usually don't graph a line with the points we created. We graph a line with the here. Thanks. This is a 3, 2. I got off. Thank you. We usually graph a linear equation with slope and y-intercept. And here's how we say it. We say the graph begins at y is 4. Up 1, 2, 3, 4, make a dot. And then the slope is negative 2 over 3, which means to go down 2, right 3. So from there we go down 2, right 3, make a dot, and draw a line. Any questions on number 1? So we're not dealing with a rational graph, so we weren't concerned with the asymptotes. Any questions on that? Okay. Very good. Number 2. Number 2 is a rational graph. If we compare that to the parent function y equal 1 over x, then we see that we've added 2. Adding 2 means that it's going to do what? Shift up 2. Now, your asymptotes for a rational graph would have been the x-axis, y-axis. But instead of being the x-axis now, it's going to be at y is 2. A y only is a horizontal line. So the whole thing shifts from the x-axis up 2. So that horizontal asymptote is y equal 2. you see, shifted up 2. There was nothing going on with the x there, so there was no horizontal shift. So our horizontal asymptote remains x equals 0, which is the y-axis. Now, don't draw this, but we know that what's happening then is we're going to have something like that going on, okay? We just want to get some good points for it. Now, you can't just find 1 or 2 points and get that. You got to find a bunch of points, okay? So what we're going to discover is kind of how to find those points. All right, so to build a table, we start with x because it is the domain or the independent variable. We solve for y because it is the range or the dependent variable. What y is equal to goes in the middle, so in the middle we have 1 over x plus 2. Now, just because we've never dealt with this, we're just going to throw in the old faithful x's and see what happens to us and plot them and then discover that we're going to have to do better than that, okay? But let's just do that to start with. Let's put in the old faithful x's of -2, -1, 0, 1, 2. So if I plug those in, I'm going to have 1 over -2 plus 2. 1 over -1 plus 2. 1 over 0 plus 2. 1 over 1 plus 2. 1 over 2 plus 2. Oh, yippee, yippee, we have lots of fractions. They're going to have a lot of fractions with this, okay? So we just have to deal with them. So, what's -1/2 plus 2? 1.5. What's -1 plus 2? +1. What's anything divided by 0? Undefined. What's undefined plus 2? Still undefined. What's happening at x equals 0? There's a vertical asymptote. That's why y is undefined at that point. Or that's why there's an asymptote at that point, whichever way you want to say it. There's an asymptote because y is undefined, or it's undefined because there's an asymptote. Okay. 1 plus 2 is 3. And 1/2 plus 2 is 2.5. Now, let's just plot those and see what we get. We've got -2. And I've got to remember, my origin is here. I'm going to just dot my origin. That's not a point. So from there, I need to go -2 up 1.5. -2 up 1.5. That puts me about right there. Okay? And then I've got -1, -1, which is left 1 and up 1, which puts me about right there. So now I've got a point here and here. And then I've got 0 and undefined, which you can't plot that. And then I have 1, 3, which will be to the right, up 1 and up 3. That ends up there in that other part. And then I've got 2 and 2.5, to the right, 2, up 2.5, which is about right there. Okay? This little point right here is the origin. I'm going to make it black so it won't get confused. That's not really enough to get a real good look at what we want to do. So we could stand to choose some more. Now, is everybody done with those? Because I'm going to get those out of the way so we can choose some more. See how come I made it so long? You may have to go to the bottom of the page before we're done or something. Okay? All right, so we were at -2, right? So maybe we need to go -4, -3. And we were over there at 2, so maybe we need to go 3 and 4 and see what that does for us. So if I plug that in, I'm going to have 1 over negative 4 plus 2 and 1 over negative 3 plus 2 and 1 over 3 plus 2 and 1 over 4 plus 2. We just have to keep throwing in points and try to move those points into those curves some more, you see. So negative a fourth plus 2 is 1 and 3/4. And negative a third and 2 is 1 and 2/3. And a third and 2 is 2 and a third. A fourth and 2 is 2 and a fourth. Now, what we're going to find is we're throwing some more numbers in, and that thing's making creepy little, it's creeping. We're not making big moves here. We're just barely off of the last point we had. So we're going to learn something about how to do something better. I'm doing this on purpose so you can see, okay? So we got negative 4 and 1 and a third. So negative 4 and 1 and 1/3. Which is somewhere in there. Oh, it's 1 and 3/4. There we go. Which is somewhere about, it's a little higher. Okay. So we got closer to that asymptote. That's good to see. Negative 3, 1 and 2/3. Negative 3, 1 and 2/3 is here. 3, 2 and 3, 2 and 1/3. 1, 2, 3, 2 and a third. That's approaching this one. We're kind of getting close to the blue asymptote with all these numbers. Okay? 4, 2 and a fourth. 1, 2, 3, 4, 2 and a fourth. Now you can see that what we've got is this going on. We're getting this and we're getting this. We're still not getting those points close to the green asymptote. Well, how are we going to get those? We've done more negatives and more positives. Well, rational kind of throws things upside down. It kind of reciprocates, doesn't it? So what are we going to have to plug in to get some stuff closer to the green? Fractions. So that they'll reciprocate and get big. Okay? So we're going to do that. So let's choose negative 1/4. Oops, I need to go the negative 1/2. Excuse me. Negative 1/2, negative 1/4, positive 1/4, positive 1/2. So we figured out if we just kept making negative 5, 6, 7, 8 or positive 5, 6, 7, 8, we're going to be getting closer and closer to the blue, and we're not getting closer and closer to the green. But because this is rational, we have to choose some fractions to be able to make that happen, you see. So now we've got 1 over negative 1 over 2 plus 2. 1 over negative 1 over 4 plus 2. 1 over 1 over 4 plus 2. 1 over 1 over 2 plus 2. And we don't need a calculator. When you divide by a fraction, what do? Let's say the rule. When you divide by a fraction, you multiply the reciprocal. Dividing by negative a half is the same as multiplying by negative 2. What's 1 times negative 2? Plus 2 is 0. Dividing by negative a fourth is the same as multiplying by negative 4. So you can have negative 4 plus 2, negative 2. 1 divided by a fourth is like 1 times 4. 4 plus 2 is 6. 1 divided by a half is 2. Plus 2 is 4. See how we did that? Reciprocal. This actually says, so if this will help you, it says 1 over says the reciprocal of, doesn't it? The reciprocal of a half is 2. Plus another 2 is 4. Okay? So now we're going to plot those. Negative 1/2, 0. Negative 1/2, 0. Now we got over there close to the green. Had to throw in some fractions. Negative 1/4, negative 2. Now we're really hugging it. That helped us out. 1/4 and 6. 1/4 and 1, 2, 3, 4, 5, 6 is really hugging it here. 1/2 and 4. And now we can finish our little rational. It never crosses those asymptotes. It's getting closer and closer, but it never really hits. And so we played with things to figure out how to get some good data points to come up with a decent looking rational graph. Okay? Any questions on number 2? Yeah, just we want to hug the blue a little and hug the green a little, and then we can zip it in there pretty close. Okay? So you're going to have to make a good many points, and you're going to throw in some positives and some negatives and some whole numbers and some fractions, obviously. Okay? Any questions? Yes. This is a rational graph. A rational graph is of the form. A rational graph is of the form y equal 1 over x. So when there's an x in the denominator instead of the numerator, it's rational. Now, number 1, the x is not in the denominator. So here the x was in the denominator. It could be x plus 6 down there. It could be x plus 6 in that denominator, and it'd still be rational because it's still in the denominator. There it would shift to the left 6 and up 2. So you'd have 2 asymptote changes, a horizontal asymptote change and a vertical asymptote change. Yeah, so if it's... Yeah, so if we had that, then you would have y equal 2, because it shifts up 2, and x equal negative 6, because it shifts left 6, the opposite of what you see, because you undo what's happening to x and you do what's happening to y. Okay? Okay, let's talk about that. The question was, we thought it would happen the other way. Okay, what we're saying is, this is what's happening to the y's, correct? You're right. What's happening to the... Now, what's happening to the y's, okay, the y values are your up-down values, right? So, all of the up-down values are going to be bigger by 2. So, instead of them being here, they're going to be here. So, our up-down went up by 2, and a y only is a horizontal line. Yeah, boy, you really have to think through it, don't you? Yeah, but you almost got me tripped up there. I had to stop and go, okay. Okay. But you're right. That's good to do that, though, because you have to stop and think. It's tricky. All right. Okay. Number 3. Number 3, is there an x in the denominator? No. There's no fraction. So there's no asymptotes here. What kind of thing is number 3? It's a polynomial of the second degree, which is a quadratic. Now, if we're going to build a pretty table for a quadratic, we're going to be on page 195A of the Algebra 1 book. Okay? I'm going to give us some room here. Now, remember what we did? We said, first of all, we'll get this set up. But what's the first thing we did to come up with a nice, pretty table for a parabola? We found the line of symmetry. Y'all need to go back and study the tests that we've already taken. You are losing it as fast as we're getting it. Okay? The line of symmetry equation is x equal negative b over 2a. Now we're cooking. So we're going to have the opposite of my b, which is 3, over 2 times my a of 1. And so I get a negative 3 over 2. So that's the same as negative 1.5. So my line of symmetry, this is not an asymptote. It's the line of symmetry for my parabola is that x is equal to negative 3 over 2. Understand that? The vertex is somewhere on it. Now, here's what we said we were going to do. We were going to pick a table of 7 points with the vertex in the middle. We know what to call the vertex x because it is the same as the line of symmetry x. The line of symmetry x was negative 3 over 2. Therefore, the vertex x is negative 3 over 2 because the vertex sits on the line of symmetry. And then we said, don't write this down, we're going to find the vertex and then we're going to find 3 left wing points. If we're going to find 3 left wing points, then we need to be to the left of the line of symmetry. So we want the first 3 integers less than the vertex x. What's the first integer less than 1.5? This is negative 1.5, right? What's the first integer on the number line less than that? Negative 2. And the next least. And the next least. All right. So to build a pretty little table for a parabola, we're going to find the line of symmetry. And then we're going to let the line of symmetry x be our vertex x. We're going to choose 3 points to the left of the vertex x, which will be the first 3 integers less than the vertex x. We're going to plug those in and find the solutions. Don't forget to put that negative 4 in parentheses. Some of you didn't do that on your parent function transformation pages and you kept messing that up. Okay? Plus 3 times negative 4 plus 2. Negative 3 in parentheses square plus 3 times negative 3 plus 2. Negative 2 in parentheses square plus 3 times negative 2 plus 2. My vertex, negative 3 over 2 square plus 3 times 3 over 2, negative 3 over 2 plus 2. Now, we're not doing any of the other bottom points. We're gonna reflect those bottom points. We're not going to calculate them. We're going to reflect them. So we're going to do the calculations here. Negative 4 squared is 16. 3 times negative 4 is negative 12. 16 and negative 12 is 4 plus 2 is 6. Negative 3 squared is 9. 3 times negative 3 is 9. 9 minus 9 is 0 plus 2 is 2. Negative 2 squared is 4. 3 times negative 2 is negative 6. 4 plus negative 6 is negative 2. Negative 2 plus 2 is 0. Negative 3 over 2 squared is 9/4. 3 times negative 3 over 2 is negative 9/2. If you change that to fourths, you got negative 18/4. So you get 9/4 and negative 18/4 is negative 9/4. Negative 9/4 is negative 2 1/4. Negative 2 1/4 plus 2 is negative 1/4. You can throw it in the calculator if you want to. It might give you the same answer, I don't know. Anyway, so we're going to plot those now. Notice what we found. We found the vertex, negative 3 1/2, negative 3/2, which is your negative 1.5, negative 1/4. Now my origin is here, so I'm going to be about right there. Okay? There's my vertex. My vertex sits on my line of symmetry at negative 1.5, negative 1/4. Okay? Now, the red stuff is my 3 left wing points, okay? So I'm going to have one at negative 2, 0. I'm sorry, negative 2, 0. Let me get back on it. Come on. Right there we go. Negative 2, 0. I'm going to have one at negative 3, 2. And I'm going to have one at negative 4, 6. So I've got my line of symmetry, I've got my vertex, and I've got 3 left wing points. Now I want to find my right wing, and I want it to match my left wing. That's why I didn't just make up numbers. I'm going to use my left wing to figure out my right wing. Now, in the graph, we know that however far this point is from the line of symmetry, it's going to have a sister point on the other side. And however far this is from the line of symmetry, it's going to have a sister point on the other side. And however far this point is from the line of symmetry, it's going to have a sister point on the other side. We want to find those sister points. Now, the sister points have the exact same y values, right? So that means this one's going to have a sister point with the same y value. This is going to have a sister point with the same y value. And this is going to have a sister point with the same y value. And to find the x's, I'm seeing how far away from the line of symmetry it is, right? I can mimic that in my table. Watch how I mimic that in my table. How far away from the line of symmetry is that? From negative 1.5 to negative 2 is down 1/2. Now what's the opposite of left 1/2? Right 1/2. So that one's sister point, instead of being left 1/2, can you see that going on in the picture? I'm going to go to the right 1/2. So negative 3.5 plus 1/2 is negative 2/2, which is negative 1. And then I'm going to look at the next. From there, we don't have as much fraction. The next sister point was 1 more lower. The next left wing point was 1 lower. So I'm going to make it sister point 1 higher than the negative 1, which would be 0. And the next left wing point was 1 lower. So I'm going to make it sister point 1 higher than the last, which would be at positive 1. So I found perfect reflection points using that process that we see on page 195A in the Algebra 1 text. So this next point will be at negative 1 and 0. The next point would be at 0, 2. The next point would be at 1, 6, and you can see that we calculated properly to have a reflection across that line of symmetry. Okay? Everybody say we got the pretty little parabola. Okay? Keep your head up. You keep your head up, please. All right, any questions on number 3? All right, well, we're getting close to out of time, so maybe we should stop there. Number 4 is another rational graph because it has a variable in the denominator, and so it will have asymptotes, and then we'll deal with that next time. Thank you.